does what it's supposed to do. And few simple logic libraries. So that's how we create the phase zero activity. And at that point, there was very little work on stressing the device and reliability of it. It just to show that we have a scheme of things that works. After that comes a process device integration qualification. This phase, only few lots of wafers. A handful of wafers through the pilot line, no other commitment beyond that. It's a small group of people, about 20. Mostly process and device engineers and technicians, with some support elsewhere. Like if you do a diffusion, stain it, scanning electron microscopy and that kind of thing. The TEMs, SEMs, that kind of, some rudimentary supports elsewhere from journals. That's about the extent of the phase of this activity. When we move to the next phase, it's much more elaborate. At that point, we engage a whole slew of other organizations. We engage not only what is called reliability engineering, we engage product engineering, we engage those who are going to do some library work in logic, those who are going to do some memory, some circuit design, some architectural group. So we increasingly employ other groups of people. And then we also have to go by the qualification requirements, at least 10 lots of wafers processed, and then the beginning of stress testing and stress qualifications. Because those will determine how robust possibility are in the technology integration scheme as well as the devices. And basics, can we make these circuits and can we do this kind of things and this sort of things, and what kind of performance gain we want, this sort of things. After this, we go to a phase 2, which is far more engagements. At that point, we are basically putting a lot of wafers through the production system. And then it is going through much larger. The product engineering group, there is a much bigger group of people. Then there is an assessment by other research, like IBM research centers. Those folks come in. They claim that something extra has to be done, tested. We want to verify, want to make sure that our great minds are also working with you and making sure that you have not misstepped something, etc., etc. So it's a much bigger engagement, and that goes for 2 years. And once that gets done, then volume production of the initial set of parts, the first parts that's urgently needed in the systems. And those parts qualifications. And at the same time, when that goes on, this phase, we also do how to ramp up volume production, how to address the yield and cost of every product, how to control all the defects in volume production environment, and how to transfer the technology foundry to other foundries. IBM used to have not only the foundry in Burlington, but also in East Fishkill, also in Germany, also in France, also in Yasu, Japan. So there are 5 foundries. So the technology will be transferred everywhere. And these experts would come from all places. They will learn all that nuances of the technology, they will replicate what we have done in the local setting. So this is how the dynamics of the technology, all phase technology and design manual. At every phase, we generate, the phase 1, phase 2, phase 0, we generate something called a design manual. It puts on a piece of paper the recipe, the learning, and how to use that for design point of view, whether it's circuit design, system design, whatever. The rudiments of that, it's all outlined, and that is being used by everybody. And that is a very well-guarded secret for the industry. So that if nothing leaks out and no competitor can get access to it. So one of my purpose in this class, to give you some flavor of what the design manual means, which you will not learn from any textbooks, and how it is put together, and what are the critical elements. I'll give you that flavor, because I see, if not directly, indirectly, you will be the champion of the industry for the future in India. So that sociality, that discipline, that engagement would be something relevant to you as you go through this class. So I put much emphasis on that. That's why after the basics things, I will go into quite a bit on that, because that's how I lived my many years of my career. Okay. So as you can see, that the resource requirements, manpower, tools, wafer starts, qualification, test, reliability, and all other dependencies are all clearly had to be spelled out and justified. And that's all translated into dollars and cents. So, just to give you an idea, that the top management is committed when they're saying, okay, go ahead, do it. This is all being done behind the scene. That they are committing literally billions of dollars of resource. So it's a risk they take. And if they are not foresighted to take the risk, no gain. So it requires the wisdom and foresight of business leaders to take such risks. And so, it's a question of trust. In business, you hand it over to people whom you trust. So that's how it works, everywhere. It's human beings same everywhere. So anyway, what's important to recognize that the resource gets multiplied. By the time it goes, it's far greater than 10 times when it starts. When it starts here, please. Okay. So because the resource commitment, it's a big decision. It's not a trivial decision. So that is something that you recognize that makes him the US often the leader in creating, helping, fostering, moving the technology. Because they have a lot of very bright businessmen. Very bright businessmen. And that's the key to them, and their ability to integrate talents, their ability to put them together for the common goal. That's what makes electronics so much fun and so much interest. So this is really what I wanted to pass on to you. That we need those kind of, and hopefully some of you will be those visionaries. Create new horizon for India. And that's the reason I come here. I have no reason to be here, other than my emotional attachment to Bengal Engineering College. I came for you. You will be. Okay. Now the technical details. We'll go through that and hope we can cover this fairly quickly because there's a lot of information here. And you can always, I welcome you later on to go through them carefully. Ask me questions later in subsequently in formal or informal classrooms, doesn't matter. But I wanted to give you a taste of how industry develops technology, what it takes to be successful, and so that you can pioneer the future of India. So, we came up with a set of targets, which we, our best of thoughts that we can possibly deliver. So, we're going to go, as I said to you, the proposal was we're going to do this submicron ULSI technology. We'll test it out in both 5 volts and 3.3 volts using the same sort of macros or designs that is being qualified by the previous generation of technology. We're going to go down. The claim was that we could sort. There was a proposal I had to tell you this. Our immediate managements were very leery that I'm taking too much of a risk. And so they were trying to convince the big bosses that, we already qualified this technology. Why go take this risk? We can sort. We can sort. You know what sort means, right? At the end of a certain process of technology at the end, you test. You have a scheme of testing. By test, you figure out that if I want a DRAM access, let's say SRAM access, just to say, of 10 nanoseconds. How many chips in a wafer can give me an access of 9 nanoseconds? Just because there's enough variation here. We designed it back in those days in at least 3 sigma tolerance, probably 4 or 5 sigmas. That was later on it became 6 sigma. All technology has to meet 6 sigma requirements. That was but back in those days that was, if you have done 3 sigma, that's okay. So there's enough tolerance, right? Enough variation. So one of the proposals went to the about, why don't we just sort the CMOS too? That way we don't have to take risks. And we will deliver those that corresponds to less than 1 micron channel, 0.9. They were not happy with that, so it ruled out. But there was a deep concern whether we can make this thing work or not. So, gate oxide thickness, we said we're going to scale. For 5 volts is this. And for 3 we'll scale on the floor of oxidation, gate oxide, when you grow the oxide. So EOT will have 2 variations. 20 nanometer and 14 nanometer. So we scale that. And we said we're going to scale the gate, polysilicon gate. As you know, that the way we did that, we defined the gate. And before we put the sidewall, we'll show you the pictures. Before we put the sidewall, we implanted lightly doped diffusers. Then we put the sidewall, we then put the substrate. This is how we integrated. So, what we wanted to do is that we said, The polysilicon, the best they can do, so-called step and repeat systems, can do about minimum feature 1 micron. So for engineering purposes, it will be like 1.2 micron. That was the technology going into production. We said, well, we'll tweak it a little bit. We'll do this and we'll do this. But we'll reduce the channel length by the so-called DILDD type approach. And we'll reduce overlap. I'll show you a little later. I ran into some problem and I fixed it. So we'll reduce overlap capacitance to speed up the device. Remember what we spoke earlier? You have to reduce the channel length, you have to reduce the parasiticals. Okay. Both device series resistance as well as overlap capacitance to get the performance of the device. And oh, by the way, in order to do that, and you have to control the lateral profile, we change the junction technology. So we will have the junction technology lightly doped, heavier doped, significantly shallow. We're scaling it. In terms of vertical features, in terms of background doping, enhance some N-well and P-well doping, P and P N-well doping.